So now let's take a look at the behavior of a gas if you have a fixed amount of gas at constant pressure. Okay, so we start again with our equation PV equals nRT, since that summarizes the behavior of the gas. If pressure and number of moles are constant, okay, let's put all of those constants on one side of the equation and put all the variables on the other side. So our variables are V and T, right? So I can rearrange this equation, PV equals nRT. So I want to put my T on the left along with the V. So I divide both sides by T, that cancels out the T. And I want my pressure on the right, I want the constants, all the constants on the right. So I divide both sides by P, and that cancels P from the left side. So I have V over T is equal to NR over P. Okay? So what am I saying here? Volume over temperature is equal to a constant times a constant times a constant. So volume over temperature is a constant. So V over T is a constant. Okay? So for a fixed amount of gas at constant pressure, we say that the ratio of volume to temperature in Kelvin is a constant. What does that mean? That's a definition of what we call direct proportionality. When the ratio of two things is a constant, then you say those two things are directly proportional. So the volume and the absolute temperature of a gas, we say, are directly proportional. What that means is if temperature goes up, then so will the volume. If you double the temperature, you double the volume. You triple the temperature, you triple the volume. Okay? Temperature gets cut in half, the volume gets cut in half. Okay, so in layman's terms, basically what we're saying is gases expand when heated. You increase the temperature, you increase the volume. Okay, but this is just a more precise way of saying it. And you have to realize, it's very important that you realize that the temperature that we have to use for these calculations has to be in Kelvin. Okay, and so a plot of volume versus temperature is called at constant pressure. So if you were to plot volume versus temperature, and you're going to plot all the data you collected at a given pressure. So if you graph all of that, okay, you get what's called an isobar. That means all of these data points were collected at the same pressure. Okay, so if I have here, let's say, if I have V1 here and T1 over here, and let's say this is V2 and T2 over here, okay, then you can say V1 over T1 equals V2 over T2. Okay. Any 2 points on an isobar. Why is it called isobar? Remember, barometric, it's related to pressure. So bar means constant, isobar means constant pressure. All right, so V1 over T1 equals V2 over T2. So that's what a plot of directly proportional quantities look like. What would be your y-intercept here? It's going to be 0. Why 0? Because here you say V over T is equal to NR over P, right? Or you can say V is equal to NR over P. Let me rewrite it this way. Both sides, multiply both sides by T, then times T, right? Look at this equation right here. If I were to plot volume on my y-axis and temperature on my x-axis, NR over P is a constant, so that's going to have to be my slope, and I must have a straight line, and y-intercept here has to be 0. Okay, so volume versus temperature at constant pressure will be a straight line, and the slope happens to be equal to NR divided by whatever the pressure is. And it's going to have a y-intercept at the origin. Okay, now historically, measurements of temperature were made in Celsius. So when these experiments were originally done, volume was plotted versus temperature in degrees Celsius. And what they found was all of these isobars, okay, would all intersect over here. So if I have a different pressure, I might get another one over here. So I get different sets of isobars. All of these isobars, it will turn out they would all intersect down here Okay, it will have an intercept of negative 273 degrees Celsius. Okay, so that would suggest that the volume of a gas would be extinguished when we get to negative 273 degrees Celsius. And so that is defined as our absolute zero. And that is what you would call 0 Kelvin. Okay, and so basically what we did is we just shifted whatever your temperature is, you add 273 to that to get your Kelvin temperature. So negative 273 plus 273 would give you 0 Kelvin. So all we've really done is we shifted our left axis. It's, if you remember your algebra, this is like translation. Okay, translation to the left. Okay, so this is Charles's law. This is known as Charles's law, the relationship between volume and temperature at constant pressure for a fixed amount of gas. So let's look at a simple example here. You have a 10-liter sample of gas, initially at 300 Kelvin. You heat it to 600 Kelvin at constant pressure. What will happen to the volume? So you can see this is relating volume and temperature at constant pressure. So V1 over T1 must be equal to V2 over T2. Okay, and so what I'm looking for? Final volume. So to solve for V2, I just multiply both sides by T2, right? And so what do I get? I get V2 equals V1 over T1 times T2. V1 is 10.0 liters. And I'm going to put these two together here. T2 is 600 Kelvin over T1, which is 300 Kelvin. So 600 over 300 is 2, so 2 times 10, that gives you 20 liters, right? Kelvin cancels out. So essentially what happened here, you double your temperature, you double your volume. Okay, so 300 times 2 gives me 600, 10 times 2 gives me 20. So you start off with whatever volume you have, you multiply by a temperature factor. That would be greater than 1 if the temperature went up, and it would be less than 1 if the temperature went down, and to get the final volume.